Hi, my name is Kevin Worsley.
Hello, my name is Dominic Holloman.
The title of our senior project is a low-cost emotive animatronic with a convolutional neural network on embedded platforms. Our advisor was Dr. Mohamed Ali. The word animatronic is a portmanteau of the words animated and electronics, and animatronics are often utilized in entertainment purposes where live actors aren't viable or repeatability would be too much of an issue for a live person. Animatronics are seen in a wide variety of industries, often the themed entertainment industry, things like museums, amusement parks, or interactive experiences. The photo on the right is a animatronic called Tom Morrow, one of the many productions of the Walt Disney Company for their theme park division. In terms of toy manufacturing, which is another major player of animatronics, usually they're used in commercial grade or large manufacturing scale of toys. On the left side here is a Baby Yoda figurine recently produced by Hasbro that features plenty of animatronic movement in the eyes, mouth, and ears.
These enterprise applications often suffer from the same problems. The animatronics in amusement parks are large, complex devices, costing anywhere from thousands to millions of dollars. The animatronics used in amusement parks are even more complicated when they need to interact with people. So if a child wants an interactive robotic toy, much of its design has been simplified from its amusement park contemporaries. The sacrifices made for mass-produced children's toys are seen in the animatronics' lack of features and behaviors. These toys often do not directly interact with the user, instead relying on pre-programmed behavior controlled with the remote.
So the goal of this project was to create an animatronic figure that resembles a flower. This animatronic will take the facial expression given to it by the user, as well as a couple vocal cues, and then mimic the emotion of the user back at them through a fun and whimsical animation played on the animatronic.
For the hardware, a Raspberry Pi Zero runs the machine learning algorithm, communicating with a PIC microcontroller. This PIC microcontroller acts as the main director for the system, interacting and controlling peripherals like an LED dot matrix, microphone, speaker, and more. This is then all housed on our own custom PCB.
The figure utilizes a custom convolutional neural network, or CNN, to perform the facial emotion classification. It was designed in TensorFlow and deployed on the Tensorflow Lite in the flat buffer format to more efficiently run on the embedded system of choice, the Raspberry Pi Zero W. It uses OpenCV for the image preprocessing step and a Haar Cascade-based facial detector to pull the face out of the image and prepare it for processing. So let's go over a little bit about how a convolutional neural network works. CNNs generally tend to excel in vision applications as they're most suited toward pattern recognition tasks. In this case, that's exactly what we want, is classifying a typical pattern of a facial emotion. So our CNN starts with an input image and passes through a convolutional layer first. This convolutional layer will pass a filter over the image and generate a feature map of the pixel's similarity to the pattern on the filter. Now, generally, when we start this training process, the filter will be random, but as we train, the filter hones more and more in on useful pattern data and becomes a more targeted convolution operation. An activation comes next, which in this case is the ReLU activation, which removes any negative values from the convolutional step. A negative value would indicate that there was no pattern identified in the pixel group that it looked at, so we don't want to save that data as it's not very relevant to our pattern. A batch normalization will be next, which reduces noise and variance in the sample, helping to make sure that we're not throwing off our data through any unnecessary noise. A max pooling step will come last, which shrinks the feature map generated in the convolutional step to only the relevant information, and by doing this, we decrease the size of that feature map, making it more computationally easy to crunch, as well as making sure we're only passing on relevant data. Once the convolutional step is complete, we then flatten the convolutional layers and plug them into a densely connected layer system. So densely connected layers are the more traditional neurons that you would see in a neural network. These densely connected layers, or neurons, will start usually with a large amount, but as the model trains and funnels down toward the output layer, the neurons decrease and eventually result in the output layer, which is the amount of classifications that we want. In the case of our project, we wanted 4 classifications, so our output layer is size 4. A softmax activation on the output layer determines the final result and returns the classification with the most likely chance. So here's some information about how I implemented the CNN. So I used TensorFlow for this with the Keras library as the front end to help speed up the construction. I constructed about 25 models for this project and determined that model 19 was our most successful. These models were judged on accuracy, or how often it could return the correct classification given a completely unbiased dataset. It uses 5 convolutional modules, which simply consists of 2 convolutional steps, 2 batch normalization steps, and 1 max pooling step. This is repeated 5 times before flattening and being passed to the densely connected layers. There are 9 of these, starting with 4,096 neurons, passing down to eventually 16 neurons before we flatten it out to the final output layer. This model is very similar in structure to VGG16, which is an already existing and well-researched pattern recognition model implemented as a convolutional network. So here are the results of Model 19 running on the development machine. The large image is what was captured on the webcam with the classification printed in real time on the image, and the small image was the image processed and then passed to the CNN, so we can see how the image is shrunk, grayscaled, and cut to the correct dimensions. So once we confirmed the model worked in the standard TensorFlow format, we converted it to the TensorFlow Lite format. This would give us better performance on the Raspberry Pi Zero that we were intending to deploy the device on. So on the device, as a quick overview of how the software runs, the Haar Cascade face detector first identifies the face in the image. This is just a standard object of the OpenCV library. The face region of interest is sliced out and scaled to a 64 by 64 pixel image. The image is then grayscaled to remove any color channels, which will improve the performance of classification. Model 19 will then perform its classification, and the result is outputted to the PIC microcontroller with the classification performed. That way the larger system can take this data and handle it as it sees appropriate. In terms of performance, the image preprocessing happens in around 2 seconds, and the classification hovers around 3.7. The load time is the slowest part of this operation, at about 40 seconds, which is largely due to the low write speed of the SD card used as the main storage of the device. The Raspberry Pi does not have enough memory to load everything concurrently, and thus must make a lot of expensive disk writes. So here we have the system running on a Raspberry Pi Zero. So we're going to take 5 pictures here, and we'll show the classifications they produce. So the first one, I made a neutral expression, and we see after the pre-processing that it returned the correct classification. The next one was happy, and we can see that the pre-processing step usually takes a much shorter time than the classification. The next face I made here was angry. And that's correct. The next face I made here actually was not a face at all. I moved my face out of camera, and we can see that the system is able to recover after being unable to find a face. And for the last one, I'll do a happy face again, just to show the system's flexibility.
Now to the hardware. This system was designed to take the output from the machine learning algorithm and create a convincing emotional response to the user's emotions. During the design phase, each system was physically prototyped on a breadboard, and its functionality was confirmed. Initially, the emotional recognition, master control, and sound systems were to be implemented on an FPGA and ARM processor. Due to out-of-date drivers from the manufacturer, a new system was designed using a Raspberry Pi Zero as a machine learning processor and 8-bit PIC microcontrollers as peripheral controllers. A PIC 18F4321 acts as the main processor, controlling the RGB LEDs, servos, LED dot matrix, microphone, and interfacing with the Raspberry Pi Zero. A secondary PIC 12F1822 is used as a direct digital frequency synthesis audio controller, creating sinusoidal signals for audio output. This PIC 12F is controlled by the PIC 18F. The final circuit is shown here. After designing and prototyping each system, a PCB was designed. To reduce costs, this circuit was implemented on a 3 3/4 inch by 3 3/4 inch 2-layer PCB. The final PCB, with and without power and ground planes visible, is shown here as well. Once the PCB was designed, a 3D model of the toy was created for 3D printing. The first version is shown here. The bulb contains an LED dot matrix, as well as an RGB LED strip. The stem is moved by a servo in order to show off its dance. A camera is hidden within on top of the base plate, and a PCB is mounted below the base plate, with the speaker also being concealed within the pot. This all then plugs into a 12-volt AC adapter. Controlling this hardware is the software running on the PIC 18F4321. First, it checks the microphone for an audio event. If nothing's going on, the flower displays a sleeping animation. But if something is, if someone's talking to it, it reads the output from the machine learning algorithm. That output is fed into a lookup table. If that output has not been received before, then the flower displays a song and a dance, depending on the emotion. But if that output has been occurred before and happened recently, then all it does is show off its facial animations. You can see a demo on the next slide.
Hello everyone, here's a demo of the hardware aspect of a single project. Due to coronavirus, this was not put on the PCB, but we did still do all the design work for that. Also, for demonstration purposes, the line that would have been connected to Kevin's work on the Raspberry Pi has been instead just shifted over to a toggle over here. And then the audio trigger, which is a microphone over here, has been also shifted to a small toggle so that I can show you the actions. Once an audio event has been triggered, we'll see a response in the RGB LEDs, which would be an LED strip, but for this demonstration, it's a singular LED. Another PIC microcontroller, which handles the direct-to-digital synthesis for a nice output sound wave right over here. Another response would be the servo doing a little dance if it's happy. And finally, the facial output is seen over here. So right now it's turned off. We power it on. We'll see that it's in a neutral state, which is supposed to be asleep. So when it's not receiving an audio trigger, it is asleep. So right now you can see the sleeping face. But if we make it happy, so we're going to switch this to happy, and we're going to switch this to on. It does a little dance and it makes a little song. But let's make it sad. No happy dance. But it does show us a nice little sad blue light, and it played a sad little tune. So that's the hardware overview of the senior project. Thank you very much for watching.
In terms of future work for this project, we'd first like to be able to combine the elements in the physical space. COVID-19 prevented us from actually constructing the device in person, so we'd like to make that our top priority. Another step would be to modify the driver we used in the LED dot matrix, as it used a proprietary 16-bit control code, which is not SPI compliant, so we'd like to upgrade to a driver that is SPI compliant for more robust access. We'd also like to increase the stability of the emotion detector, namely through generating the model again based on a larger dataset, which would include more variants and samples and make the model more robust to changes. We'd also like to improve the quality of the Haar Cascade facial detector for more variance in its environment. Now this could be accomplished by training our own version of the detector rather than relying on the default OpenCV dataset. We are very proud to present our project, and thank you for listening.